So, students, today we will take up this chapter of continuity. As a matter of fact, on my last lecture, I did tell you that I will be taking differentiability today. But then what I was observing is that that's the second section of this chapter. So we will continue with the continuity, and exactly this is what is in your course. And we will be taking your first exercise also. But prior to that, let me take up this definition and this properties of continuity. So as I have already told you that most of the results as far as in continuity are concerned, they will be derived straight away from what you have done in limits. Because when we will see the definition of continuity, what we will find is that it is nothing but if the limiting value of the function is equal to its functional value, then we say that the function is continuous at that point. So quickly coming to this definition of the continuity, so we say a function, first we will define continuity at a point and then continuity over an interval. So first I am defining continuity at a point. So let fx be some function, let fx be some function, be a function with domain D, with its domain D. Okay. Now see, we say fx is continuous at a point say C naught of domain if limit x tending to C naught fx is equal to fc naught. See, this is the definition. Now see, so what essentially is being said is, and this is the definition of continuity at a point C naught. So see, what needs to be taken note of is that continuity at a point will only be defined when the function is defined at that point. If the function is not defined at that point C naught, then see, its limiting value will not be equal to its functional value, and as such the question of function being continuous at the point C naught doesn't arise. So students, please mind it that if at all you are you have to check whether a given function is continuous at a given point C naught of its domain, then you have to first of all ensure that the function should definitely be defined at that point C naught. If not, then of course see, function can never be continuous at that point. So this is the prime condition for continuity to exist, for function to be continuous. Now, in limits, you have already seen that whether the function is defined at that particular point or not, it hardly matters. Because therein what we, in limits, see, if we are checking the limit of a function at a given point C naught of its domain, then function need not to be defined therein also. Even then the limiting value will exist. The case in point of course is that you take the example x square minus 4 upon x minus 2. Here see, obviously if you are checking the limit at x tends to 2 of this function, what is your function? X square minus 4 upon x minus 2. Then see, here the function is not defined at 2. But its limiting value exists because x square minus 4 on factorization will give you what? X minus 2, and x plus 2, x minus 2 will cancel. Because x minus 2 is not equal to 0, because under the limiting condition, what the important thing which we have taken note of is that x can come nearer to any degree whatsoever one feels like, but it will never be equal to 2. So with that aspect and with that important we can cancel it in the numerator and denominator the factor x minus 2. So eventually this will be x plus 2. So you are basically calculating limit x tending to 2 x plus 2 for all x not equal to 2. Please mind it, this thing will cancel only when x is not equal to 2. So for rest of the values, see, it will be 4. So limiting value will be 4, because when you are in the neighborhood of the point 2, then the value will be approaching towards 4 either from the left side or from the right side. So that's the important difference between continuity and limit. In limits, please remember whether the function is defined or not at the point where the limiting value is being calculated, that there it hardly matters. But in continuity, if the function is not defined at the point where you are checking the continuity, then please mind it, the function will never be continuous. It has to be defined at the point. And the second thing which we have to see is in continuity is that if a function is continuous at a given point C0 of its domain, then the limiting value should be equal to the functional value. Now see here, we will discuss something more in detail. Now coming to the point of this thing here. Okay, I would like to enlighten one thing here. When we say limit x tending to C0 fx is equal to fc0. Now, before we elaborate on this particular aspect, we had to define left hand limit and right hand limit. Let us see what it exactly means and why they are essential. Okay, suppose my function is defined, my function fx is defined over a closed interval a to b. And suppose I say, and if I had to suppose check the continuity at the endpoints, and suppose my function fx is simply x square, fx is equal to x square. You know that fx is equal to x square is a polynomial, and as such, it will be the limiting value of a polynomial, we have earlier proved, is always equal to its functional value. So that is to say that the limit of this function fx is equal to x square, which happens to be a polynomial, will certainly exist anywhere in its domain. And what is the domain of this function? The entire real line. Fine. Now see, but I say my function is a real function with its domain being closed interval a to b. Okay. Now see, here if I had to find my limit, say at a fx, and I have asked you what it is, or if I ask you what is the limit at the extreme right hand point, that is as b, then what you will do. Now see here, if at all their limits are existing, then see here what you will find that suppose if the limit is say L. So in this case, limit x tending to a fx is equal to suppose L. Now here you will take any epsilon interval of L, and given to that epsilon interval of L, you will find a delta neighborhood, deleted delta neighborhood of A, with such that whenever x falls within that deleted delta neighborhood of A, your functional value should fall within the epsilon neighborhood of L. Now here see the important thing what is there here. Suppose this is L. Suppose this is L1. L1 suppose is a positive number, I have chosen some epsilon, so this is the mark L1 plus epsilon and this is the mark L1 minus epsilon. This is the epsilon neighborhood, or in other words what it is the epsilon neighborhood of L1. Okay, so what I have to find it out? Now suppose A is my negative number, I have to find out a delta such that this is A minus delta, this is A plus delta, and A of course is deleted from here, minus from this deleted delta neighborhood. What I am doing it is deleted delta neighborhood of A minus A. Only the middlemost point I have denoted. So now see that this thing visible or not? No. Okay, students are not getting it. Okay, I have to write it on the top because what I am saying. Okay, let me just please do it like this. Now I think is it visible? Now it's visible. Okay.
Yes, sir. Yes, sir.
Okay. Now I will see because on my iPad everything is coming clear. It has got a broader screen. So now okay. So point is that here. I will choose some epsilon neighborhood of L1 and then I have to find a deleted delta neighborhood of A. Now see, on this side, on the left side, that is from A minus, this is A plus delta, mind it, this is A minus delta. From A minus delta to A, see the function is not defined. Function is defined from A to B. So see here, when saying that there exists a deleted delta neighborhood. So here see this will become meaningless because here the function is not even defined. So that is the point that here only what is defined is from A to A plus delta. See this much of portion is defined. From A onwards it is defined. Your function is defined from A to B in a closed interval. So that is why see at times we had to make use of the concepts of left hand limit and right hand limit. So here see, we will not take the entire delta because here A minus delta to A plus delta it becomes a meaningless quantity. So therefore we will restrict ourselves only to A plus delta. A to A plus delta. A to A plus delta. Mind it, here we will be taking A to A plus delta and this particular fact we will be writing how limit x tending to A plus because when we are on the right side of A, then this is symbolically written as A plus fx. Then of course see this is L1. So here see if function is defined over the closed interval AB, then we can't go on the left side of A. So here getting a deleted delta neighborhood of A will not very good thing to say because from A minus delta to A the function is not even defined and as such these concepts of left hand limit and right hand limits comes into play. For right hand limit see here if I had to calculate the limit at B then again same thing what I will be doing it. I suppose this limit is L2. Suppose this limit is L2. Let me rub it. Suppose this limit, my function is defined wherein from A to B. A to B. See why we fx its domain is what? Closed interval A to B. Okay. Now see what is happening. If I suppose this is 0, this is my B point. I will take any epsilon. No, it is not B point. Suppose limit x tending to fx is say L2. Then suppose this is the point L2. Then what I do? Normal, I have to take epsilon interval. So this mark will be corresponding to L2 plus epsilon. This mark will be corresponding to L2 minus epsilon. Then this is I will choose. This epsilon is discretionary. Now once I have chosen this epsilon interval of L2, then what I have to show? Yes, if at all the limit exists, then what I will show? Suppose this time B is positive. B is positive and say this is this thing. Now see, I have to find a deleted delta neighborhood, that is suppose this is B plus delta, B minus delta, and from it the element B of course has to be. Now taken out, but this is what is required in the limits. But in continuity, B will certainly be there. So that is another aspect that we will come later on. But right now, what I am trying to explain you is that why at all we need this left-hand limits, right-hand limits. It is because of this thing. Because at times, suppose our function is not defined on the left side or the right side of the points. So here on the right side of B, the function is not defined, only on the left side. So here when I say extending to B, so what the point is that from B to, in this interval, B to B plus delta, the function is not defined. So this part will be meaningless. This part will be meaningless. And as such here, instead of saying limit extending to B, fx is equal to L2, it is better always to say limit extending to B minus. Because on the left side, the function is defined. And as such here, we will not take B plus delta. Our deleted delta neighborhood this time will be what? It will be B minus delta to B. This will be our deleted delta neighborhood. That is, whenever x lies in this deleted delta, in this neighborhood, then functional value will fall in the epsilon neighborhood of L2. This is what the limit at extreme points will imply. And this is what left hand limit and right hand limit exactly means. Otherwise, see, for all of the rest of the points in the interval, in the open interval A to B, see, the function will be defined on the left side, on the right side as well. So therein, of course, see, you can find if for a particular point at C0 suppose limit is. So therein, of course, see, you can find a deleted delta neighborhood of C0, that is C0 minus delta to C0 plus delta neighborhood can always be found if we are in a position to find always a deleted delta neighborhood of C0. Then, of course, provided epsilon neighborhood of the limiting value is taken, then we say the limit exists. So this is the concept. This is the concept. Now here, so we will now be introducing the definition of left hand limits and right hand limits. So okay, so please do write down quickly. So I think it is a sub part. It is a sub part and of the definition of the limits. It is the sub part of the definition of the limit, and quite simple if we have been able to. So what is how we define left hand limit? See what is the symbol? Limit x tending to suppose a, and left hand limit I have to define. So I will write a minus. A minus. A is a real number. Left hand means what? This time this is my 0 mark, therefore this is a. So I will be approaching a from the left side. This is what it means. And then my whatever my function is. So if this limit is L, then we say that what you say. Now we are defining. We say left hand limit definition of, now what is being given to you is definition of left hand limit. LX limit. Please, I try to understand. So it will be exactly on the same lines. So you will say limit x tending to a minus fx is equal to L. Left hand limit of fx is L if same thing, if for every epsilon greater than 0 there exists a delta greater than 0 such that modulus fx minus L is less than epsilon whenever. Please see, this time slight modification will be here. Earlier we used to write 0 is less than x minus a, but here what we will be writing is fx minus whenever x is okay. We will not write x minus delta 0. Earlier we used to write x minus a is less than delta. But this time we are not going to write it because mod x minus a, this inequality less than delta means what? A minus delta to a plus delta. So that thing here, that change we had to make it out. So what it would be? It would be if x is the element of a minus delta to a. That's all. because here delta already we are delimiting. We are taking the open interval. So 0 greater than 0 is less than x minus a. See, earlier what the thing is, we used to write 0 less than x minus a is less than delta. Now this thing is already taken care here because a is excluded in the open interval, and rest of the things, the other part we don't want, because 0 is less than mod x minus a is less than delta. Mod x minus a x, see this inequality 0 is greater less than x minus a simply means that x can't be equal to a. So this is one thing, and this other inequality, this right, this second one, x mod x minus a is less than delta. This simply means x is the element of what? A minus delta to a plus delta. That's all. So now this thing we had to curtail. This part we had to curtail for the obvious reason that the function is not defined on the right side of a, right side of a. Similarly, if we had to define right hand limit of the function of fx at a, then what we will, the definition would be same thing. We say limit, symbolically, what is the symbol? X tending to a plus. A plus means we are approaching the number 8 from the right hand side. We say limit x tending to a fx is equal to L if for same thing, say language, if for every epsilon greater than 0 there exists a delta greater than 0 such that what? Yes, mod fx minus L is less than epsilon whenever what? Whenever, this time we had to be cautious. Earlier, see, in general limit what we use, right? 0 is less than x mod x minus a is less than delta. But here what we will do, if x is the element of a and a plus delta. That's all. See, this is the change which we will be doing it. So I think, and if both left hand limit and right hand limit we include, then it amounts to the same thing. Of course, there in the middlemost element we will be ignoring. So now see, with these two definitions in mind, we will now prove an important result, and that will be, see how we will be employing that result in the question for actually ensuring the continuity at the given point. At the given point, see what the thing is. First, see, I will be proving one theorem. That is, if limit x tending to a fx exists is equal to L. This exists. Then this implies what? This implies both left hand and right hand limit will exist. This implies limit x tending to a plus fx and limit x tending to a minus fx exist, and each of them will be equal to L, and both of them will be equal to L. See, this limit is equal to this limit is equal to L. Means both left hand limit and right hand limit will exist, and both of them will be equal to L. And proving this thing is quite a simple affair if you have understood the definition, because proof is very simple. This way only we have to prove it. This is our theorem. And this is our theorem. This not a theorem but a result. And so I will not write theorem because this is an obvious result. And this is a by result of the definition of the limits. Because proof, since limit exists, limit x tending to a fx is equal to L. This implies what? This implies for every epsilon greater than 0, there exists a delta greater than 0 such that mod fx minus L is less than epsilon whenever 0 is less than mod x minus A is one is given to you. One is given to you. Now see here, you see it is inherent. If so, this much of thing is already happening. So this thing is also happening. So see, if this thing is less than delta, so this thing will also happen whenever, see, either a to a plus delta or a minus delta to a occurs. Whenever x is the element of itna or x is the element of this thing. So this is what your left hand limit is. This thing is your right hand limit, and this thing is your what? If x is the element of this thing and this thing is happening, mod fx minus L is less than epsilon. For every epsilon, if see you can find a delta for every epsilon, then means left hand and right hand limits are existing. So this is not a theorem. This is obviously a conclusion straight away which you can derive from it. But then what about the converse part? What about the converse part? Yes, that also we have to look in. Now see, converse means, see, if both left hand limit and right hand limits are existing. See, converse is important, and that see, you will have to make use of in the proving the important results at times. So what the thing is, now converse. Let us see the converse of this statement. Converse simply implies means if both left hand limit, left hand limit and right hand limit of a function exists at a point C naught of domain then limit will also exist. Limit x tending to a fx is equal to also will also exist. No, if both left hand limit and right hand limit of a function exist at a point C naught is element of D, and more so ever see one thing I missed altogether, and both of them are equal, both of them are equal. That is yes, limit x tending to a plus fx is equal to L is equal to limit x tending to a minus fx. Then limit x tending to a fx exists and is equal to L So this is the converse statement, and we will prove this thing. Now see, at times what you will find, yes, both left hand limit and right hand limits are existing, but they are not equal. So under those circumstances, the limiting value at x is equal to a will not exist. So students, when in a good number of questions, whenever you have to check the continuity at a given point, so what you will do in your this 12th class, that you will check whether the left hand limit exists, you will check whether the right hand limit exists. If both of them are existing, and more so ever both of them are equal also, then of course see, you can safely conclude that the limit will exist. But if see what the possibilities could be, that either of them is not existing, then of course see, the limit will not exist. Whether the left hand limit is not existing or right hand limit is not existing, then see, the limit will not exist. Now suppose both of them are existing, but the case is that both of them are existing but both of them are not same, then also the limit will not exist. Only the limit will exist when both left hand and right hand limits, they are existing and they are equal. Then of course see, then we will say that the limit exists, and this limiting value will be same as that what is being obtained by the left hand limit or right hand limit, and this is what precisely we will prove. So now what we are taking, that both left hand limits and right hand limits are existing, and they are equal. They are equal. And then what we will show, that yes, that the limit will exist. That the limit will exist. Okay. So this is what we will prove. So proving this converse statement is also an easy thing, provided we know the definition. So since see in your this class 12th, you would be basically in the questions of continuity at the class 12th level for board examination. This particular aspect, of course, will be used widely, so you be careful about it. Now see, so what is given? Now given is limit x tending to a right hand limit is equal to left hand limit x tending to a minus fx, and both of them are equal to each other. Each of these limits are existing, and first of all they are existing, and moreover they are equal to each other. Then to prove, yes, limit x tending to a fx is equal to n. This is what we have proved. Now see. Now from the definition, says limit x tending to a plus fx is equal to n. This implies what? This implies for every, see I will write this small, for every epsilon greater than 0, there exists a delta greater than 0 such that what is happening? Yes, mod fx minus L is less than epsilon whenever yes, x is the element of a to a plus delta. And likewise, limit x tending to a minus fx is L. So what this implies, for every epsilon greater than 0, there exists a delta greater than 0 such that, same thing, mod fx minus L is less than epsilon whenever yes, x is the element of a minus delta to a. Now see, say this is result 1, this is result 2, combining 1 and 2, what we will get? Combining 1 and 2, what we will get? That, yes, please see, that limit x tending to, yes, if we combine it, then what we will get? That yes, x tends to a, because here see, if we combine it, what it will eventually give me? X is tending to a minus delta, x is tending to a minus delta to a, so it will be x tending to a minus delta to infinity. So this is that limit x tending to a fx is equal to L if for every epsilon there exists a delta greater than 0 such that yes, fx minus L is less than what? Fx is the element of what? A minus delta to a plus delta and minus a. Because this a is ignored in both 1 and 2. So, and this is, this particular thing you can well write to be nothing, but fx minus L is less than delta. Sorry, x minus a is less than delta. Yes, x minus a is less than delta. So this theorem is proved. So this converse part is also proved. So please remember that whenever you had to prove that whether the function is continuous at a given point c naught, you calculate the left hand limit, you calculate the right hand limit. If both of them are existing, and then of course see, there is a fairly good chance that the limit will exist. And then if you check it that both of them are existing and simultaneously both of them are also equal, then you will say that our limit of the function exists. Limit of the function exists. So this is all about this thing, left hand limits and right hand limits. Now, and the definition of continuity we have seen, and the definition of continuity we have seen. Now, then next is continuity in a given interval. Continuity in a given interval. Continuity in a given interval. In a given interval. So, what is this? Simple. If function is continuous throughout at every point of the interval, then we say that the function is continuous in the given interval. So, if function is continuous, if function is continuous at every point of the interval, at every point of the interval, then we say that function is continuous in the function is continuous in the given interval. In the given interval. Okay. So hardly anything. At each point of the interval, if the function is continuous, then it is said to be function to be continuous in the given interval. Now next what we have to see, okay, we will take this thing a bit later, infinite limits. Okay, yes, see, at times see, okay, let me do a little bit of questions, then of course see, we will take infinite limits and limits at infinity, because that is also same thing on the same line. But before I take this thing, let us, so that we can attempt the questions, let me take a little bit of theorems as far as this endeavor of continuity is concerned. And the first theorem will be that if f and g are functions, now write down these theorems here. Theorems. If f and g are continuous functions, functions at a point say C naught, then following result will follow. Then number one, f plus g is continuous. Continuous at where? Point C naught. At point C naught. 2, f minus g is continuous at C naught. Third is the product fx dot gx function is continuous at C naught. Likewise, fourth is fx upon gx is continuous at C naught. And the most important of these, is that so that we will take differently, because that will be a result pertaining to function of functions. We will see that when a function of function is a continuous, so that will be continuous if internal function is continuous at the point C naught, and the external function is continuous wherein at g C naught. Okay, so that we will take it separately, but these four theorems, of course, see, are straight away the derivation of the theorems of the limits. So we will take the proof of them. They are very simple here. Okay, and now let's take the proofs. Yes. So what is given? First theorem, very simple, direct offshoots of the theorem of the limits. So what is given? F and g are continuous at the point. So limit x tending to C naught, fx is what? Fc naught. Because what should happen? If it is continuous, therefore the functional value at C naught will be equal to the limiting value. So limiting value is equal to the functional value, and likewise for the other function, limit x tending to C naught, gx, what it will be? It will be g C naught. So this is given to you. To prove Yes. Fx plus gx is continuous at c naught, x tending to c naught. So this limit should be equal to what? Fc naught plus gc naught. Gc naught. This is what we have to prove. So now simple proof. Proof is very simple. One line proof, because the main thing was because from the limits. In the limit we have already shown that the limit of the sum of two functions is equal to sum of their individual limits. So with that understanding, limit x tending to, yes, let me write here, limit x tending to c naught fx plus gx. Yes, this will be equal to what? Limit x tending to c naught fx plus limit x tending to c naught gx. And here you will write limit of the sum of two functions is equal to sum of their individual limits. Limit of the sum of two functions is equal to sum of their individual limits. Now, as soon as you write this thing, here you please write limit of sum of two functions, sum of two functions, two or more than two, finite function, two or more functions is equal to sum of their individual limits. Sum of their individual limits. Individual limits. So as soon as, and this limit is what? Fc naught plus gc naught. And the result is proof. Theorem is proof. Likewise, if you have to prove that yes, this second theorem, limit say x tending to product of this thing, fx naught into fx into gx. Limit of this thing, given is this thing, individual limits exist, then you have to prove that the product of this is also continuous. How we will prove? So what you have to prove? This thing is fc naught into gc naught. And again, see, very simple. Take left hand side. Left hand side will be what? Exactly the left this much of thing. Isn't it? So left hand side, let me write once again here, because limit x tending to a rather. Limit x tending to a at any c naught. Okay, c naught. Here the point chosen is c naught. So it will be fx into gx. And then see, in the limits, this is what? Product of their individual limits. X c naught fx into limit of x tending to c naught gx. And here you will quote in here that limit of the product of two functions is equal to the product of their individual limits. This thing please do write in the bracket, and this is being already given to you, fc naught into gc naught. So this is a interesting. So this is how you have proved the third theorem. Likewise, if it is fx upon gx naught, then what do you have to prove? Limit x tending to c naught fx upon gx. Of course, the gx should not be equal to 0, will be equal to fc naught upon gc naught. Fourth part. So what you will do? It will be x upon, and then again you will quote this thing, and then this will be upon this thing. So it is, of course, see, basically the theorems of the limits, and that's why, see, if you know the theory of these limits, then of course this continuity comes handy to you. So this is all what you will do it. Now I will take another important result which you will be using here, and that will be pertaining to the yes. Okay, so that will be a limit continuity of the function of function. Next heading is continuity of function of function. Continuity of. But before I take continuity of function, I will explain you one very good result, and that has been very well explained even in your book. Now see, suppose fx is some function which is defined only at one point. Which is defined only at one point. Okay, at say c naught. And means if domain consists of only singleton point C naught. And if somebody asks you limit x tending to C naught fx, whether this will exist or not. See, please see, it's a good question. So yes, what will be your answer? This is one good important result. Here see, I repeat it. Your function is defined only at one point, and that point is C naught. And what is being asked from you is that is this function continuous at C naught? Yes, answer will be yes, it will be continuous. For the simple reason that, see, what will happen? Here, let epsilon be any small number, then what the delta will be? You can take delta to be any real number, because what will happen? See, fx minus L, what your condition requires? That this should be less than epsilon, rest of the things of course, whenever what should happen? Whenever C0 is less than x minus A is less than delta. Or in other words, x should be the element of what? A minus delta, A plus delta minus A point you will ignore. This is, now please see this definition concerning. Now here see, at no point the function is defined. Only at function, sorry, it will be C naught. Because C naught you have taken. Please make it C naught. Please make it C naught. So now see here the function is defined only at the point C naught. So limit will also exist as far as continuity is concerned. C naught you will take only since it is defined. So x should fall in this interval. So when x is not defined, x is only defined at C naught. So obviously you can't take any point irrespective of whatever delta you can take, because see, function is not defined anywhere. So point is that here this function will be continuous at C naught. Now with this understanding, we will take the continuity of function of function, please see, and then we will start taking the question, because that this will be the last theorem, continuity of function of functions, Yes. So let f dx be a function of function. Let f dx be a function of function. And gx be continuous. Internal function is gx be continuous at C naught, and fx be continuous at gc naught. Okay, this is what has been given to you. And what you have to show that function is continuous. That f then show f gx is continuous. F gx is continuous at x is equal to C naught. Proof, simple. Again see, we will be employing the theorems of the limit, because all these results we have already proved in the limit. Okay, how? Limit of function is what? Limit x tending to a, f gx is equal to limit, yes, internal function you put t tends to, yes, I will show you, f t, right, and here limit of x tending to, yes, C naught, gx is what? It is continuous. So it is gc naught. So what do you use to write t tends to b? So here b is what? If you recall your theorem, it is b. This internal function where it goes x tending to c2. So this is b. So limit t tends to b. Now, so this will be nothing but f gc naught, because t tends to g. This is continuous. This has been given to be continuous. Please see, it has been given. Function is continuous at x is equal to c naught. What does it mean? It means limit that show that gx be continuous and fx be continuous at g c naught. So limit of f x and x tends to where? G c naught. So this is continuous, so this is f g c naught. So this is how we have established the result. This is how we, so if in a function of function, if internal function is continuous at c naught and external function is continuous at g c naught, then the function of function is also continuous. This is a very important theorem which we shall be using in a few questions of your book, but then see, at times you use it frequently without actually knowing it that you are employing this theorem. You are using this result of continuity without actually knowing that yes, you are using this result. Now we will quickly take up the questions of your exercise. Yes, only one thing has been left out, and that is the continuity in infinite limits. Let me take it also, because then of course we can easily take up the questions. So one more things, I will not take limits at infinity, I will only take limit at infinite limits. So let me take infinite limits. First you infinite, because that is there in your syllabus also, infinite limits. So what actually will happen? At time c, what will happen? That the limit of a function will either be plus infinity or minus infinity. When such is the case, you say that this is case corresponding to limits, infinite limits. Infinite limits. And at time c, what you have to calculate? Limit x tending to infinity plus minus fx. And now see, it could, suppose this is some finite number, and then there can be a most general case where you can have A option, B option, where see you have infinite limit as well as limit at infinity, you are limit at plus minus infinity, and fx is also equal to plus minus infinity. So that could also be a case. Now all these three cases, we would be seeing that what their respective definitions will turn out to be. So first let me take the first definition. Please see, I'd like to forewarn you that since I am uploading my videos on my YouTube channel, the link has already been given to you. If not, then today again I will be sending it to you. Please watch it again and again. Once you have been able to understand this theory, then I tell you, rest all the things becomes too simpler for you to understand. See, complicated questions have certain tricks. At times, see, one student, at times you have to apply hospital rules and all that, which are not given in the syllabus. So that additional things you will come to know. Solving question is one thing and understanding theory is another thing. Once you understand the theory, you have so much of confidence, brings within yourself that see all these questions you can take easily. So once again my request is that please visit my videos and see to it that the theory part is very well clear to you. And then see the questions given in, there are 34 questions today. I was seeing your book, and all these 34 questions are basically verbal questions, verbal oral questions. Even in your board examination you get verbal questions provided you are strong in theory. Okay, so what this definition will be? Now see what the thing is. First let us understand that what actually happens. That here see, because the problem is that here you cannot take epsilon neighborhood of L. Infinity is not a number. Infinity, from infinity if you subtract something, still it will remain infinity. If infinity you subtract any finite number, it will stick. So here see what the problem is, why we had to modify our definition is that here see infinity, we can't take epsilon neighborhood of infinity, because infinity minus epsilon infinity plus epsilon is again infinity. So it is a null set basically. So it doesn't make a point. Infinity is not a number. So this is what you can't say, and that's why this whole thing which you are telling, making use of is not a good thing to do. So what the idea is, see fx is, suppose it is plus infinity, I try to make you explain the other definition when the case is corresponding to minus infinity. Fx is equal to infinity means when you are approaching towards a, either from the left or from the right, then your functional values are becoming too large, are becoming greater and greater. Now this concept of greaterness, as I have repeatedly been telling you, and at the very first lecture I have made this aspect clear to you, that this concept of greaterness is a comparative one. See, you can't always say that whatever a given number is too big enough. No, it can't be, because any big number you think of, still you can think of a number which is in comparison to which the earlier thought of big number becomes relatively too small. So these, so what we are trying to say is that here, see, please, I tell you what we will try to incorporate our definition, because see, the concept should come to you. It means we will say that limit is tending towards infinity if see any number, any large positive number we think of, say n, then see we can find a deleted delta neighborhood of A, such that whenever x lies in that deleted delta neighborhood of A, then functional value should be greater than that number n. So this is what modification we are going to do it. Similarly, if it is going towards infinity, then see we will take a very small negative number, and then we will say if corresponding to any small negative number, howsoever is small, on the negative real side, we take any small number, and still if we are in a position to find a deleted delta neighborhood of what? A, such that whenever x falls within that deleted delta neighborhood, then your functional value should be less than that number, and that number say n. So this is what precisely we are going to do in our definition next. So first definition is, yes, you please write down, and to understand it also, we say limit x tending to a fx is equal to in plus infinity if given any number, any positive number m, capital M, howsoever large, we can find a deleted delta neighborhood of A such that fx is greater than m whenever what? 0 is less than mod x minus a is less than delta. This is the definition. Had it been minus infinity, then what would have been the corresponding changes? Then of course we would have said limit x tending to a fx is equal to minus infinity. Minus infinity if what? If given any small negative number m, what? Again there exists a delta greater than 0 such that fx is what? Less than this time m, if what? If x is the, if yes, you can write 0 x minus a is less than delta. Yes, so this is what, when you will say that limit x tending to a fx is equal to minus infinity. So this is how we would be taking the changes. Later two definitions we will take up later on. Okay. Today see, I will take few questions straight away. Then we will come to the next day, because already 1 hour time has been left. Okay. Or you do one thing. We will try the questions later on. Today you please go through all these definitions. Limit at infinite. I will take one more definition. Limit at infinity. Limit at infinity, or So let me do that also, and then see the more general case also we could have taken it. Now suppose we take limit x, though this is not in your syllabus, but first fx is equal to L. So what it means? It means you will say, we say limit x tending to infinity fx equal to L if for every epsilon greater than 0 there exists a existed a number n, such that what mod of fx minus L is less than epsilon whenever what is happening, whenever x is tending to it, whenever x is greater than n. That's all. And likewise, limit x tending to minus infinity fx is equal to L when if for every epsilon greater than 0 there exists a number, this time of course it will be negative, that exists a number. Now this number here it will be positive, it can be negative also, that this is number n, such that what should happen? Mod of fx minus L is less than epsilon whenever what? Whenever, yes, x is less than n. So this is how limit when x approaches plus infinity or minus infinity is defined. And then see, you can have the most general case. Of course, see, I will stop it there. That is when limit is infinity and limit, this limiting value is also infinity, and finite limits as well as this thing. So that case we are not taking it up. But with a hope and expectation that see, you first go through all this theory, because see, if you look in today, see, in any of these theorems of this continuity, we have not done anything new. We have only applied the theorems of the limits. So my request to you is, because see, I am telling you that this exercise will be a verbal exercise. You can do the questions very easily. And so with this request, I stop it here. I will be uploading my video immediately after 2 or 3 hours. And on my channel you can share it. Bhavesh sir, you can share it if your students are not having it. And so thank you. We will meet day after tomorrow again. Thank you.